I share the screen with the presentation. As on previous lectures, I will switch between presentation, desktop, board, Visual Studio, and so on. Now I share the first screen of my presentation, and you can see that the topic of this lesson is numerical differentiation. This is a plan of this lesson. We consider the problem statement. We discuss about the Taylor series approach to differentiation, and we investigate some numerical differentiation formulas. But before we start to discuss about numerical differentiation, let's review formulas for analytical differentiation of the functions. We consider some formulas of differentiation of the first lesson. Let's review the main formulas and the main functions, the very important functions and very important formulas for numerical analysis. Let me switch to the board. I write something on the board now. On the first lesson, we review some rules of differentiation. If we have a function x power n, what is the derivative of this function? X power n derivative. What is the derivative of this function? You can write your answers in chat. You can answer by microphone. X power n. First derivative. You can type your answers in chat. And also I can write you these examples, these questions in Visual Studio in the form of comments. Maybe I can use not only the board, but I can write the rather simple formulas here in Visual Studio. Yes, right, this is correct answer. The first derivative of x power n equals to n times x power n minus 1. Okay. X power n, it's a basis function for constructing the polynomials. That's why this function is very important. The next important function is exponential function, e power x. What is the derivative of e power x? Also, we consider this function on the first lesson. Oh, I share the screen. Let me share the window. Yeah. What is the answer? E power x first derivative. Yes, you're right. This function has the same derivative. That's why this function is very important for numerical analysis, because a lot of examples can be written using exactly this function, exponential function, because it has the same derivative, e power x, the same derivative. And let's review trigonometric functions. We will use it not very often, but it's better to review it now. Derivative of sine. Derivative of sine is cos. Derivative of cosine is sine, with minus, of course, with minus. You can find the rules, these rules of differentiation in any book, any page on Wikipedia. We consider not general rules, but these very simple rules. But you can type differentiation rules and find the page on Wikipedia where you may find all of the rules. Well, we will use these two functions as examples, because it's rather simple to find the derivative. Well, and what is the problem of this lecture? The problem is that sometimes we should calculate a function, a derivative of a function that we don't know. Of course, if we knows nothing, we don't know nothing about the function, we cannot calculate the derivative. It means that we don't know the formula, but we know the values of this function at several points. And using these values, we should somehow estimate the derivative at these or other points. This goal is also written in my presentation. Now I switch to the presentation. So it's written exactly that I told you. Suppose we don't know a function. We don't know a formula. but we know only a few values at some points. Say x0, x1, x2, and so on, xn. We know n plus 1 values of the function at n plus 1 points. And the answer is not answer. The question is, can that information be used to estimate derivative f prime c, where c is some point? And the answer is yes. Yes, we can do it. If we know only the values of the function, this information will be almost useless for us. We can estimate the derivative only in the case when we make some suggestion, for example, that f of x belongs to the class of polynomials. If f of x is a polynomial of degree at most n, then the values at n plus 1 points completely define the function f of x by the theory of interpolation. I hope that you remember from the previous lessons, 2 previous lessons, that we can take n plus 1 points and find the polynomial using these n plus 1 points of degree n. If we have 2 points, this polynomial will be linear. If we have 3 points, the polynomial will be quadratic, and so on. In general case, we have n plus 1 points, and using these n plus 1 points, we can find the polynomial of degree n. After that, we can compute the first derivative of this polynomial. And then we can use p prime of c as estimation of f prime c. We can use a derivative of a polynomial as estimation of a derivative of a function. This is a general idea of numerical differentiation. Again, let me review all the steps. We have n plus 1 points. We can build a interpolating polynomial that passes through these points. We can find derivative of this interpolating polynomial, and we can use derivative of a polynomial as estimation of derivative of a function. This picture illustrates this idea. Suppose that we have n plus 1 points. Suppose that we have 5 points. 6 points. 6 points numbered from 0 to 5. x0, x1, and so on, x5. These are these points. If we know that the function that passes through these points is continuous, this information is useless, because there are infinity many number of continuous functions. For example, f1 is a piecewise linear function that passes through these points. f2 is another function that passes through these points, some kind of polynomial, for example. f3 is another function that passes through these points, and so on. If we know only these points, that there are infinity many number of functions, and this information is useless. But if we fix that the function is a polynomial of degree 5, it completely solves, in theory, the problem, because we can build a interpolating polynomial using 6 points and find the derivative. But we exploit this idea to derive different formulas for numerical differentiation. But some simple formulas can be derived directly from the definition of the derivative. What is the definition of derivative? Also, we considered this information on the first lecture. The first derivative, by definition, is a limit when h tends to 0, such a relation f of x plus h minus f of x over h. The real value of the derivative we can obtain when we compute the limit when h tends to 0. Actually, we cannot compute the limit on computer. We can compute it only using pen and paper, theoretically. But now we discuss about the computing mathematics. Some methods, some techniques that we can implement on computer. But if we look to this formula gives us an obvious way to generate approximation of f prime x. Let's remove the sign of the limit. Let's take small but fixed value of h. In this case, we can say that the first derivative will be approximately equals to f of x plus h minus f of x over h. This is so-called first order formula for numerical differentiation, and this formula number 1, is known as a forward difference formula when h is greater than 0, and backward difference formula when h is smaller than 0. And this formula gives us exact approximation if the function is linear. This fact is very simple. Let's prove it, because the proof is also it's very simple to prove it. Now I switch to the board, I close the presentation. Let's switch to the board and let's prove that this formula gives us exact value of the first derivative for linear function. By the way, what is the exact value of the first derivative for a linear function? Suppose that the function is ax plus b, linear function, first derivative. What is the exact value of the first derivative? Ax plus b, first derivative. What is the exact value? I think this question is very simple. We recall the formula of finding the derivative of x power n, but here we have x power 1. And the question is, what is the first derivative of ax plus b? You can answer using the microphone, you can answer using chat, but I'm waiting for your answer. This question is very simple. What is the real value of this derivative? Good, very good. The real value of the derivative is a. Very, very simple case. The real value of the derivative is a. But now, let's consider the first order difference formulas. F of x plus h minus f of h over h. X is the sum point, and h is the some fixed step. And now let's consider the case when f of x is equal to ax plus b. If we apply this formula, we will have here a x plus h plus b. I substitute x plus h formula minus ax plus b over h. As you see, b is cancelled. We have ax plus ah minus ax b cancel over h. Ax cancel too. H also cancel. And we obtain finally that f prime x of x equals to a. Exact value of the first derivative. This formula gives us the exact value. But this situation is not true for any other function except linear. We will have this that the formula gives us the exact value only for linear function. This picture illustrates this formula. Again, let's recall the first lesson where we discuss about the geometric meaning of the first derivative. The geometric meaning of the first derivative is the slope of the tangent line. If we have a point x0 and f prime of x0 will be the slope of the tangent line that pass through the point x0. This is the curve of the function. This is the point x0, and this is the tangent line that pass through this point. I see the question in chat. I say that this formula number 1, gives us the exact value only for linear function. For other functions, this formula gives us approximation of the real value. Not the real value, but some more or less correct approximation. And this approximation will be better when h will be smaller. Okay, this is a slope of the tangent line, the tangent line with some given with some slope, and these are 2 points. The point f of x and the point f of x plus h, and this formula corresponds to the slope of the line that pass through these points. I think you can imagine that if I move these 2 points closer, closer, and closer, this line will be closer and closer to the real tangent line with a real slope. The slope of this line will be closer and closer to the slope of the real tangent line. When these 2 points becomes closer, it means when the h becomes smaller, the value of h becomes smaller. Well, let's consider some basic error analysis. The starting point of error analysis is a Taylor formula, Taylor's theorem. Let's write the Taylor's formula in the following form as presented here on my presentation. F of x plus h equals to f of x plus h times f prime x plus h squared over 2 times f second derivative. Here C is some point inside the interval between x and x plus h. For the validity of equation number 2, let's suppose that the function is continuous and the first derivative of the function is continuous too on the closed interval between x and x plus h. And suppose also that the second derivative exists on the corresponding open interval. Rearrangement of equation 2, so this is it should be equation 3, but this should be equation number 2. That's right, the correct number. This is equation number 2, and this is the equation number 3. If we rearrange the terms in the equation number 2, it can be written in this form number 3. And what we will have here, if you look here, in the left-hand side, we have the real value of the derivative, and in the right-hand side, we have the formula, this formula, right? We have this formula and some error term. This will be error term. And maybe it's better to rewrite this equation number 3 in another form. Let me do it on a board. I can rewrite equation number 3 in the following form, that f prime of x minus f of x plus a minus f of x over h equals to minus h over 2 times of c. This Greek letter usually denotes the point that we don't know in advance, but we know the range. The range that this point belongs to. And in our case, in this case, the point C must be between x and x plus h. So this is the real value. This is approximation. The real value minus approximation equals to some error term. And this formula gives us the opportunity to estimate the largest error. The largest error on this interval. F prime of h minus x plus h minus f of x over h module will be smaller or equals h over 2 times maximum. Oh, sorry, I forget to write here. Oh, it should be the sign of the second derivative. Sorry, second derivative here. Maximum when c is between x and x plus a. Second derivative of c, f of c. So actually, the upper bound for the error here, it includes two terms. First term depends on h. The second term depends on the second derivative of the function. We cannot change the second derivative, but we can change h. And I think it's clear that if we take smaller h, the value of h, and the smaller value of h, we get the more precise value of the third derivative. Well, to understand how it works, let's consider the example, and I ask you to solve this example now. The example is simple. The example is simple. We discussed about the linear function, but let's consider polynomial function. Very, very simple polynomial. For example, x power 4. Okay, f of x equals to x power 4. Good example because it's very simple to find the real value of the derivative of this function. What is the real derivative? We should apply this general formula. F prime of x equals to 4x power 3. 4x power 3. And let's find the real value of the derivative at the point, say, 1. F prime of 1 will be 4. F prime of 1 will be 4. Now, suppose we don't know this formula, we forget this formula. But we know the formula of numerical differentiation. Let's take x equals to 1. Let's take 8 equals to 0.1. And I ask you to compute the third derivative at the point 1, approximation of the first derivative at the point 1, using this formula for the first derivative. Please compute the approximation of the first derivative at the point 1 using the step h equals to 0.1. You can use it, you can do it by pen and paper, you can do it using calculator. For example, I'm going to do it using Microsoft Excel, because Excel perfectly computes arithmetic expressions. What you should do to compute to apply the formula. Should find the values of the function f of x at the points x and x plus h. X equals to 1, h equals to 0.1. So it's very simple to find the values of the function. You can use calculator, you can use Microsoft Excel, and so on. Yes, I can. Yes, I can. But I hope that right now, you are trying to solve this problem by yourself. Of course, I show you the correct solution. Just a few minutes. Wait a few minutes, but try to solve it. Try to find the solution without my help. Do somebody solve this problem? Find the first derivative of the function of the function x power 4 using the formula for the numerical differentiation. Well, I think you have enough time to solve this problem. I show you how I can solve it using Excel, but you can do it without Excel. You can do it using your calculator or something else. Well, what is x in our case? Or h? H is 0.1. What is x? We have 2 points, 1 and 1.1. 1 and x plus h. Yeah. Here, you can look to this formula. I just multiply 4 times this value. I write a function x power 4. And here to d1 power 4. And in these 2 cells, I have 1 and 1.4, 641. And after that, I should apply the formula for numerical differentiation. This minus this over this. D2 minus C2 over A2. These computations can be done in Microsoft Excel. And we have the answer that the approximate solution to this problem, approximate value of the first derivative is 4.6. Let's remember that the real value f prime of x is 4. So the error will be 4 real value minus the approximation. The error is minus 0.6. It's not very large, but it's not very small. In the best case, the error must be 0 when we obtain the correct value. But let's look to the error when I decrease the step. Let's take step equals to 10 power minus 2. In this case, the error becomes 10 times smaller, minus 0.06. 10 times smaller. If I decrease h again, the error becomes again 10 times smaller. You see that the approximation now is 4.006, but the real value is 4. The approximation becomes very close to the real value. If we take h again smaller, the error becomes 6 times 10 power minus 4, and so on. The smaller h we take, the smaller error we get. And all of this is based on the formula of numerical differentiation. This formula. The error term includes here h power 1, and it makes the entire expression converge to 0 as h approaches 0. Well, if it's more or less clear, let's consider another formula for numerical differentiation. It's called 3-point formula. The precision of such numerical differentiation formula is often judged simply by the power of h present in the error term. And the higher power is better because h is a small number. For example, if we have h power 2 and h is 0.1, h power 2 becomes 10 power minus 2. If we have h equals to 10 power minus 2, then h power 2 becomes 10 power minus 4. In this assessment, Formula 1 fares poorly, as the error is of order h. A superior formula is written here, this one. This formula can be derived from two cases of Taylor's theorem. Suppose that we write a Taylor formula for x plus h, and at the same time, we write the same formula for x minus h. After that, we can subtract one of these from the other. For example, we can subtract from the first one the second one. And in this case, we obtain the formula number 3. Again, it consists of two terms. This is the approximation, and this is the error. After some simplifications, I don't want to go into details how to simplify. We can derive the final result that f of x, f prime of x equals to f of x plus h minus f of x minus h over 2h minus h squared over 6, third derivative f of c, where c is between x minus h and x plus h. This formula is very important, and let me reproduce this formula on the board. And I also write it in the form of difference of the real value and the approximation. The real value of the function of the third derivative is f prime of x minus approximation is f of x plus h minus f of x minus h over 2h. And it equals to, according to the formula that I just showed you in the presentation, h squared over 6 minus h squared over 6 times third derivative at the point c. And if I try to find the upper bound for the error, I can write f prime of x minus f of x plus h minus f of x minus h over 2h module numerical h squared over 6 maximum f of c module where c is between x minus h, x plus h. Again, this formula shows us that if we subtract our approximation from the real value of the derivative, we'll get h squared over 6 times, again, sorry, should be the third derivative, of course. I forget to write third derivative. So the maximum value of the third derivative at the point c. But the main point is that we have h squared here. In this formula, we have h power 1. H power 1, I write this one exactly. But here we have h power 2, h squared. And if h will be 0.1, h squared will be 10 times smaller. That's why we can expect that this formula will be significantly accurate in comparison with the previous one. Before we solve the example, I want to show you graphical illustration as in previous case. Let me share the screen again, the presentation. And you can see that if we have a function, we have the point x0. The value of the derivative is the slope of the tangent line, is the real value of the derivative. But we approximate this slope with the slope of another line that pass through these 2 points, this and this. These points we take with the step h, plus h and minus h. And you see that the slope of this line in general will be closer to the slope of the tangent line in comparison with the line that passed through these 2 points. These 2 points will be better. The slope of this line will be closer to the real value of the derivative. Well, now I ask you to apply this formula. This formula is written here. You can write this formula in your papers, and I ask you to apply this formula to find the first derivative for the function f of x equals to x power 4. Let's take the same example, the same function, the same first derivative, the same point, the same step, but another formula. In the first case, in the first example, we take this one. Now I ask you to take this one, this formula, and compute the value of the first derivative and compare it with the previous result. And we will see that the second formula gives us more precise solution. Please do it now. And I also do it in Microsoft Excel, of course. Did you find the first derivative? I'll give you a few minutes more. Well, you have enough time to solve the problem. let's discuss about the correct solution. Again, I solve this problem in Microsoft Excel. And again, we have the point H, 0.1. We have 3 points, 1 plus H, 1 minus H, 1, 1.1, and 0.9. And these 3 values are x power 4 at corresponding points. And finally, I should apply this formula. F of x plus h minus f of x minus h over 2h. And we have this result. The difference is minus 0.04. Let's compare the error. When we apply the first formula, the error was 0.641. Here, the error is 0.04. The error becomes 10 times smaller. And it's great. It's great that we find the value of the derivative with so small error. What happens if I decrease the step? Here, h is decreased. And here, I also decrease the step. You see that in the first case, the error decreases 10 times, but in the second case, the error decreases 100 times. And it's also excellent. We decrease the error, we decrease the step, and the error is also decreased 100 times. We decrease the error 10 times. Sorry, we decrease the step 10 times, and the error decreases 100 times. If I decrease step more, here the error is 0.006, and in this case the error will be 6 zeros. 10 times 4 times 10 power minus 6. Very, very small error. Well, do you have any questions about numerical differentiation? You are welcome to ask me any questions. If not, let me stop recording.